Okay, in this video we're going to look at the Lindstedt Poincare method, which is a way to approximate periodic solutions of the Duffing equation. So this is the Duffing equation that we've seen lots of times in the lectures. Here x is our dependent variable, x is a function of t, and we've got a few constants in the equation. We've got omega naught, and we could potentially have a constant here, k, and epsilon here is some small parameter. Okay, so we've seen equations like this in the lectures lots of times. In particular, we're going to look at the initial value problem, where at time zero, the displacement of the particle on the spring is going to be capital A, and the initial velocity, in other words, the velocity at time zero, is going to be 0. So we're releasing a mass on a nonlinear spring from rest at a distance A initially. The video is going to be split into 3 bits. So first of all, we'll answer the question, why do we need this fancy method? Secondly, what's different about this method compared to just taking asymptotic approximations of x as a power series like we normally do and sticking it into the equation, comparing coefficients and seeing what we get from that approach. So we're going to compare Lindstedt Poincare method to the straightforward approach. And then finally we'll run through how the Lindstedt Poincare method works, so how to do it. Okay, so let's quickly look at why we actually need this method. Why does the straightforward approach not really get us anywhere? Well, if we just do our normal approach, what we've been calling straightforward asymptotics, of substituting in a power series expansion of x into the Duffing equation, in other words, we say let x equal x0 plus epsilon x1 plus epsilon squared x2 and so on. Then if we compare terms of epsilon to the naught, epsilon to the 1 and compare coefficients, then the first equation we get from comparing terms in epsilon to the naught looks like this. So this is just a second order ordinary differential equation. And the second term that we get from comparing coefficients in epsilon to the 1 would give us an expression like this. Then if we solve these two ODEs with their initial conditions, then what do we get? Well, this first equation is homogeneous, it's unforced, there's 0 on the right hand side, so that's just going to have a solution that in general is a linear combination of sines and cosines. When you apply the initial conditions, you see that it's just a cos omega naught t is the solution to this one, the solution for x naught. And then the other one has a bit more of a complicated looking solution, because now we've got this forcing term of minus x naught cubed, in other words minus a cubed cos cubed omega naught t. Okay, so if you solve that, you get that x1 is equal to this expression here, but there's a problem with this expression that isn't really ideal for modelling a mass on a spring, because if we look at this term t sine omega naught t here, well, as t goes to infinity, this is going to get very big indeed. This is going to grow unboundedly. So this is what we've been calling a secular term, because it does something like this. It's oscillating, but the size of the oscillations are multiplied by t. So they get very big indeed as t gets very big. So we can't do much with this secular term because the coefficient in front of it is minus 3/8 of a cubed over omega naught. Well, a is just the distance that we release the system from. Omega naught is something that's in our original equation, so we haven't got any freedom here to actually get rid of this secular term. So the straightforward approach has got this shortcoming that as t goes to infinity, the oscillations get unboundedly big, and that's physically unrealistic. Now, the way that the Lindstedt Poincare method deals with this problem of these secular terms is to say, well, what if we insist that we want to have a periodic solution? So this is absolutely the key word here, periodic. We're just going to focus our attention on periodic solutions to this problem. Because if we do so, then we're saying that we're not going to allow any secular terms, because these secular terms aren't periodic. They keep growing as t goes to infinity. They don't come back to being the same size. So here's the problem again, exactly the same problem as before. So let's start going through how the Lindstedt Poincare method works. Well, first of all, let's consider the limit case. That's the case when epsilon is exactly equal to 0. In that case, we're not going to have this term up here, this k epsilon x cubed, because epsilon is 0, and so the Duffing equation is just going to become second derivative of x naught with respect to time plus omega naught squared x naught is equal to 0. So this is the limit case, the problem for x naught. This term disappears. Now this is a nice easy second order differential equation. It's got auxiliary equation m squared plus omega naught squared equals 0, because remember, to get the auxiliary equation for a differential equation, you turn second derivatives into m squared terms, any first derivatives into m terms, we haven't got any here, and then anything in the dependent variable, which here is x naught, just turn that into 1 in the auxiliary equation. So we've got omega naught squared times 1. So that's how we get the auxiliary equation, equals 0. That's got roots of plus or minus omega naught I. And if you've got imaginary roots of the auxiliary equation, then the complementary function, in fact the general solution in this case, is going to be a linear combination of sines and cosines. So some constant multiplied by cos omega naught t plus some other constant times sine omega naught t. And note that in this limit case, the solution here has got frequency omega naught. However, when you have got this term here, this term in x cubed, in other words when epsilon isn't 0, then it's not quite so straightforward. You can't just immediately solve this using the normal auxiliary equation type of method, because it's no longer a linear differential equation. This is a non-linear term because of this x cubed here. So although in the limit case the solution has got frequency omega naught, it's not so easy to say what the frequency is when you're not in the limit case, so when epsilon isn't equal to 0. So exactly as I've just said, for epsilon not equal to 0, the frequency becomes something that is unknown. So let's give it a name, let's just call it omega. So omega is different to omega naught. Omega naught was that constant that appears in the equation. Omega is the unknown frequency of the solution that we're looking for, because remember, with the Lindstedt Poincare method, we're looking for periodic solutions. And this inspires us to change the time variable to a new independent variable. So we're going to make the substitution tau is equal to omega times t. So omega here is the unknown frequency of the periodic solution that we're looking for, and in general that's going to depend on this small parameter epsilon. It's also going to depend on the initial amplitude a. So this is basically like defining new units of time, really. It's just a rescaling of time, this introduction of tau. So if we want to rewrite the whole equation in terms of tau instead of t, then we need to know what the second derivative with respect to t is in terms of tau. And we can get that by using the chain rule, because d by dt is going to be exactly the same as d tau by dt, d by d tau. And you know that d tau by dt here, well, that's just the derivative of omega t with respect to t, so that's just going to be omega. And then similarly, if you do this again, you get that the second derivative will be omega squared times the second derivative with respect to tau. So this is just turning derivatives with respect to t into derivatives with respect to our new variable tau. So if we then put these results into the Duffing equation, we've got this Duffing equation where we've now got independent variable tau instead of t. So we've got omega squared d2x by d tau squared plus omega naught squared x plus this constant k times the small parameter epsilon times the nonlinear term x cubed is equal to 0. So that's now the equation we're looking at. Okay, so here comes the asymptotic bit, really. So here's the equation that we had just a moment ago. Now we're going to do some asymptotics on this. So we're going to look for an asymptotic approximation for this function x. X is now a function of tau. And we're going to look for it in the kind of normal expanded form. So x is going to be x naught plus epsilon times x1 plus, okay, epsilon squared times x2, but we're just going to throw that away into a big O. We're not going to bother about the coefficients there, or what that function x2 would be, but you could carry this method on, it still works. Similarly, and this is slightly different to what we've done before with straightforward asymptotics, because we've now got this unknown quantity omega, the frequency of the oscillations that we're looking for, we're going to expand omega as well. So we're going to write omega is equal to omega naught plus epsilon omega 1 plus big O of epsilon squared. Okay, so that's a key step in the Lindstedt Poincare method, because we're saying that we're looking for periodic solutions. We don't know what the period is. We're calling that unknown period omega, and because it's unknown, we can expand that asymptotically. And now we're going to put both of those things into this equation that I've labelled star. So this is where the messy algebra starts to come in. So once you substituted it into star, you get this long expression here. And then we're going to do the normal game of collecting terms in different degrees of epsilon. So I've underlined here the terms that are going to give you products that are of order epsilon to the 0. So this hasn't got an epsilon in, this hasn't got an epsilon in, so when you multiply these two terms, it's going to give you something of order epsilon to the 0. And similarly, this term standing on its own here hasn't got an epsilon, everything else has. So the expression for terms in epsilon to the 0 is this. So omega naught squared times the second derivative of x naught plus x naught itself is equal to 0. Omega naught squared is just some non-zero constant that we were given in the equation up here. So we don't actually need to worry about this. We can divide both sides by it, and so we just have that this bracket is equal to 0, and that's a second order ODE that we'll be able to solve in a moment. Then what about terms in epsilon to the power 1? Well, again, collecting those from this long blue expression, we get this equation here. So again, this is a second order ordinary differential equation for x1. So we've got the second derivative here plus x1. And in principle, these other two last terms that are in x0, they haven't got x1 anywhere. We should know what x0 is once we've solved this first one. So you can think of x1 here in the second equation as the unknown. x0 is just going to be some function that we know. So we've got our two equations here, this one here and this one here, from substituting in omega and x as expansions, comparing coefficients and collecting terms in epsilon to the 0 and epsilon to the 1. Now all we have to do is just solve these two equations. So let's have a crack at that. What do we get? Well, this first equation I've rewritten here, and that's going to have the normal initial conditions that when time is 0, in other words, when tau is 0 now, x0 is going to be a, whereas the velocity initially is going to be 0. So that's just the initial conditions. So can we solve that? Well, hopefully yes, because that's a linear second order ordinary differential equation, so we can do the auxiliary equation again. So we'd have m squared from this term plus 1 from this term equals 0. That implies that m is plus or minus I, and so because that's imaginary, we're going to have a linear combination of sines and cosines. So x0 is c1 cos tau plus c2 sin tau, where c1 and c2 are arbitrary constants here. And then applying these initial conditions, you get that x0 is equal to a times cos tau, where a is that initial amplitude. What about the next equation? Slightly trickier. So there is the equation from the last slide. We're going to solve that with homogeneous boundary conditions, remember, because whenever you come to the next step that isn't the first step of the asymptotics, we always have homogeneous boundary conditions because we've already dealt with the boundary conditions, or the initial conditions I should say, for x0. Okay, so we can simplify this because x0 double prime, well, we know what x0 is, so the second derivative is going to be minus a cos tau. That's just twice differentiating this thing in the yellow box. And then this x0 cubed is just going to be a cubed cos cubed tau. And there's that trig identity that we've seen in lectures that says that cos cubed of tau is 1/4 cos 3 tau plus 3/4 cos tau. Okay, so putting that into the equation, we get this bottom line here. And then this term in brackets is just a constant. So if we divide through by omega naught squared, both sides, we arrive at an expression like this, where these messy looking constants I've called alpha and beta. So alpha is just this bracket over omega squared, which is this expression down here. And beta is just ka cubed over 4 divided by omega naught squared. So the question now becomes, can we solve this inhomogeneous but linear second order ordinary differential equation? So let's have a go at doing that. Don't worry too much about the detail here, but I think it's nice to see how you solve, well, to remind yourself how to solve these kind of things. So there's the equation again. Alpha and beta are just those constants that we wrote down earlier. So how do you solve such a problem? Well, you look at the auxiliary equation and get the complementary function first of all, and then you try and get the particular integral that deals with this right-hand side. So the auxiliary equation is m squared plus 1 is equal to 0. That gives you that m is plus or minus I, so the complementary function is a linear combination of sines and cosines, with a couple of arbitrary constants. We don't know what these are yet. And then the particular integral, we have some kind of educated guess at what the trial function should be. Well, here we've got terms on the right hand side that look like something times cos tau and something times cos 3 tau. So that tells us that we ought to use things like sines and cosines in our trial function. If you look at cos 3 tau, that's easy because we just want some arbitrary constant times cos 3 tau and some arbitrary constant times sine 3 tau. So that's these two terms here because of this term and the forcing term in the right hand side. And then cos tau already occurs in the complementary function. So you have to multiply by tau in the trial function. So this is stuff that you'll have done in the first year in MA 112 differential equations. Maybe you've got a bit rusty on it. Don't worry too much about how to solve this equation, but this is just a nice reminder of how you do it. So once you've kind of guessed your trial function for the particular integral, which is this xp here, you just substitute that into the equation and then simplify. So there's a few simplifying steps here that I haven't written down, but you end up with this equation here. And then you compare coefficients. So for instance, you say, well, on the right-hand side, I've got alpha lots of cos tau. On the left-hand side, I've got 2a lots of cos tau, and therefore I should choose a to be alpha over 2. And then similarly, on the left-hand side, I've got minus 2b lots of sine tau. On the right-hand side, I've got no lots of sine tau, therefore b should be 0. Same with d, and then c should be beta over 8. So anyway, we arrive at this particular integral here that says that the particular integral is alpha over 2 times tau sine tau plus beta over 8 cos 3 tau. So having done that, all you need to do to get the general solution for x1 is to add together the complementary function c sine tau plus d cos tau and the particular integral. So the particular integral alpha over 2 tau sine tau plus beta over 8 cos 3 tau. Okay, then you can look at your function that we found, our function x1, and say, right, is this periodic? So sine tau, well, yeah, sine is a very periodic function. Cos tau, nicely periodic. Cos 3 tau is also periodic, but what about this tau sine tau? That's not so good, because that is a secular term. It's going to grow unboundedly as tau goes to infinity. So because we're insisting with the Lindstedt Poincare method that we want periodic solutions, we don't want this term to be here. And therefore, we want this coefficient in front of it to be alpha. And if you look at what alpha was, then it involved omega 1. So we can pick omega 1, which we've got some control over. It wasn't in our original equation, in such a way so that alpha is equal to 0. And it turns out that the way to do that, if you go back and look at the equation of what alpha was defined as, alpha is 0 if omega 1 is 3k a squared over 8 omega naught. Then finally we can apply homogeneous initial conditions to find out what these constants c and d are here. And if you apply those homogeneous initial conditions, you get that c is equal to 0, d is equal to minus beta over 8. So we've completely now found x1, we found x0 earlier, so all we need to do to finish the question, or finish the solution, is to collect together the final result. So here it is. X of tau is equal to a cos tau, that was what we had earlier from x0, plus epsilon times x1. So applying what we saw on the last slide, you get this term is x1 plus big O of epsilon squared. You could carry on, you could go further. It algebraically gets a little bit messy, but you by all means can. And then this is where tau is equal to omega t, so really this is cos omega t, this is cos omega t, this is cos 3 omega t, and this omega is approximated as omega naught, which appeared in our original equation, plus epsilon times omega 1, and we've just said what omega 1 was, it's 3k a squared over 8 omega naught, so we've also found how the frequency varies depending on how big epsilon is and how big the initial amplitude of oscillations is a. And that really is the end of the story. That completes the Lindstedt Poincare method. We found the displacement as a function of time of this particle on a spring, and we've also found its frequency to 2 terms at least, but you could go further.